Hello, Dee.
Hi, Professor.
Good, Jack. Welcome. So we are going to start. This is our week 14 lecture B. Oh, I got the email from Kevin then. He's doing well. Okay. So FISP sequence is like this. We have 2 lectures, 75 minutes each. So 75 minutes is 3 times 25 minutes. So cool. And can you guys hear clearly? Let me see.
Yes, yes.
Yes. Okay, good. Thank you.
But a little bit.
It's a little bit low.
Yeah, a little bit low.
Low in volume.
Yeah.
Interesting. I changed my headset maybe. Is it now okay?
It's still the same. But anyway,
Okay.
we can hear it. But yeah.
I heard that okay. So it's yes, it's pretty larger.
Okay, I'll try to be loud a little bit. So Dee and Kevin and myself will cover the first day. After that, Carlos, Jack, and Howie will be the next 3 in May 6th, the week 16. Okay. You can send me chat box message if you have anything in the middle. Okay, I'm monitoring that. Okay. So let's review what we did last time. Okay, we did basically a finite time LQR, and we talked about the Riccati differential equation. And so here's the statement. Actually, it could be a LTV system, but right now let's focus on LTI. Okay. So you have a weighting matrices Q and R. Okay. Find the optimal signal. Okay. So the minimize to J. And in the end, we find out it is actually, luckily, we have a law, or optimal control law here. Okay. And we didn't consider the terminal cost. So therefore, we call this a free terminal state. We don't care about it. Let it be free. Doesn't matter. Okay. Control signal is not constrained. We're not bounded at all. Okay. So basically went through the Pontryagin minimum principle, and we have gone through several slides. Let me recall what we did. So basically, we started with a very general case, F. General case capped off, it's like that. But in many places, people use this as a L, okay? But it's okay. L stands for Lagrange, okay? So have a control system, or the admissible control. This is my set for all the feasible controls. It could be the space here. Then we'll have objective function J, which is a functional, okay? Functional. Not just a function. So if we write in this box, this is called optimal control problem formulation. And this one does not involve constraints. Okay, this is called Bowser form, meaning you have a terminal cost. Okay, so conclusion is we define a value function. Okay, for all the control within the feasible set, and for each of these, you change the maximum u. You construct a value function, okay, which is j, okay. But now we try to find out the maximum of this. So in that case, my Hamiltonian is written in terms of this one, and this is a partial v partial x times x dot. So basically, it's the v dot. Okay, this is v dot. Because this is x dot, okay? This x dot is fx ut. So we assume what's in front of f is my lambda, okay? Lambda. It turns out that the h times, of course, you usually don't have the v partial t explicitly, but let's just include that Hamiltonian. Make this one maximum, and it should be 0. Okay, so that's called HGB equation. For the canonic system equation, we're going to have 2. So this is nothing but f, okay, x ut. So this is the original state equation. However, this is new. It's called closed-state equation or adjoint closed-state equation. A free terminal case in here, s is 0. Okay, you have no terminal cost. That corresponding to setting this guy to 0. Okay, this is 0. So you can see if you put x and lambda into a vector, okay, into a vector. So you do differential equation, ODE. So you can see that half of the vector you have an initial value, okay. Half the vector you are specified with final value, okay. So then this is called a 2-point boundary value problem, okay, TPBVP. So this optimal control problem can be transformed into TPBVP. So in our case, for LQ, R, and LTI system, we put F with AX plus BU, and we have my capital F is the Lagrangian, is half of this X transpose QX plus R transpose, sorry, U transpose RU, okay? U transpose RU, so that's my F. So stationarity condition, this is giving us a connection of optimal control signal is actually proportional to my co-state. This is our second order, so meaning we are doing minimization, okay? Minimization. But how to get this lambda, this co-state? So it turns out that lambda satisfies this one and satisfies this RDE, the Riccati differential equation, okay? So this is in the matrix form, but P is symmetric. So we have n plus 1 divided by n unknown, okay? We're going to see an example today. XS is free terminal, co-state. This is like boundary value, okay? We already specified this one due to the free terminal state. So in other words, the PT, okay, PT terminal F is also 0. Why? So properties, we reviewed that is symmetric and positive definite if Q is semi-positive definite. If Q is positive definite, P is also positive definite. So we end up with this optimal control with KT, but KT is linked to P. Okay. All right. So that's it's a solvable one. So you can solve it. It's solvable. And because you are giving A, B, P, sorry, A, B, and Q, okay? So it is always possible to compute this RDE here. But remember, this is a free terminal, okay? So this is a familiar form, okay? It definitely is like a full state feedback, but with time varying gain here. And we're going to see that this is the control law now. This is a law, okay? Because we are using full state feedback. And the cost will be like this one, okay? So today we are going to run an example to show all the procedures, okay? This is important. You have to know how to do it manually, okay? And not using computer. After that, we're talking about when TF is infinity, and we are going to get ARE, stands for algebraic Riccati equation. Okay. Again, I suggest you check chapter 11 for John Bay's book. I already put it in the folder. Let's dive into this simple example. So this is a scalar single input, single state. We don't define output. Just by the way, LQR is all about state feedback. Okay, state. So we assume all the states are available. Okay. And if not, we can introduce observer. Okay, observer. So we're going to talk about that one later, probably next week. So you can see giving A, giving Q, giving R, giving this cost, giving TF, giving X0. What is my LQR control? According to this, we have a control law. This is R inverse. Here is one of R, okay? So there's R inverse. B is 1, okay? B is 1. R inverse B and X. So I know this, we know this P of T, this is time varying gain. Okay, how to do that? This is my RDE. Okay, remember A is just a scalar A. So according to the format, let's go there and take a look. It's P A transpose P. So in this case, it's -2, right? They're the same. It's a scalar. Okay, so they are the same. So it's a 2A P plus P squared. This is B is one of R. So it's 1 of R and square and then minus Q. So this Q is the same as this one. Okay. So this is a scalar form of Riccati differential equation. So you have P like this, but you cannot solve it from P0. You don't know P0 yet. No, it's not given. We don't know. It's unknown. But you do know PTF because this is terminal cost. It's free terminal state. So those are closed state equation. STF is 0. Therefore, PTF is 0. Okay. Okay. The reason is that you have lambda t defined as pxt. Or x can be anything. So this is 0, then this has to be 0. Make sense? Okay. So this is our starting point. So you can see you have ODE. You don't know initial. So you don't know initial point. You only know the final point. How you can solve it. So let's do it. So what we did is, dpt is dpt dt. So it's a dt bracket. This one. Okay. So this bracket is nothing but this guy. Okay. This is the bracket. Let's do a star bracket. So to the star bracket here. So this star bracket is also here. Okay. Also here. So you remove this on this side, then you integrate from capital T to TF. Okay. So then you integrate it with this one, PT. So it basically is the PT to PTF. While this one is 0. Be careful. So we're trying to solve this PT. It is interesting to see what is this one for. Okay. By doing some simple transformation, so basically you end up with PT can be solved as this one. Because this side is TF minus T, okay? TF minus T. Is it? Because this is 1 here. No. Okay. Yeah, that's true. Okay. But from here to here, so you assume this is something like x, okay? Something like x. So you do the integration. So you assume that you have some sort of initial state like this. Let me see. This is my already ax. This is the u, ax plus u. And the u is already minus this one. Okay. You have x like this. So therefore, you can write x in terms of p tau here. P tau here. Okay. And regarding y exponentially is a t minus tf. Okay. Why this is true? You need some work to break this one. Okay, to break this one. And it's actually not very hard. Why? Because you think about it. So you can do some differentiation like this. So if you have a dp, that you have a p plus a is t minus tf minus t. Okay. So this will give you p plus a log, okay? P plus a log is like this, okay? So then you are going to have a p plus a is e to the power of tf minus t. Of course, we have some other coefficients in here, so that's why you have e to the exponential, so you have log. So in other words, you do this one, you can split it as like P plus A, P plus B, A1, let's do this, A2. And you put another coefficient here, like A0. So you can always write it this way, okay? Then you do this one, P, T, 2, 0, okay? So you do this, you are going to have two logs, okay? You do a PFT, PFE, partial fraction expansion. You put this one as like K1, P plus A1, plus K2, P plus yes, plus A2. So you have two terms, okay? You have two log terms. So you have then, you have dp. You do this one from pt to 0. So you have log plus log. So that's why you have product. So you can solve the p. Okay? So it's not very straightforward, but it's doable, okay? It's doable. So the reason you introduce the beta is to simplify the notation. Mm-hmm. Okay, so let's assume that we can get the P, and if you put TF in here, so this is 0, 0 is 1, this is 0, okay, already. So it's true from here. P, TF is 0. Yeah, this is will be 1, 1 minus 1 is 0. Okay, so this is my state feedback. That's my P. So you can know that this can be computed in advance. Okay. Then you build a lookup table. You can put it here. Okay. So therefore, for this one, you can write your final solutions like this. This is your optimal control state trajectory. Optimal state trajectory. All right. Okay. So in this case, if you in Simulink, let's say what we should do in Simulink. Okay. What we should do in Simulink. We should solve this one backwards. Okay, backwards. You basically should integrate the system from t to 0. Okay, t0. Okay. So here is my gain. It's this one, this term. This is my pt. This is my xt. So that's to feed this one. To feed this is like what we call a joint system. This joint system will get you PT. Okay. But in PT you have something interesting. So you have Q is a constant in here. So you have P dot integrated with P, but P dot is Q minus Q here. So you have a 2AP minus plus P square. So this is a square, okay? This is square. So add together, so you get this. So this is for illustration purpose. However, if you put this one in the Simulink, it will not work. Because Simulink is like solving a bunch of differential equations, fx t, okay? So giving xt0 is x0, then you integrate from t to tf, okay? All right, but this one, you cannot. You do not know what is your p0 is not known. Not known. Okay, you don't know. You don't know. In advance, you don't know. unless you solve it backwards numerically. Okay, numerically. But fortunately, in our case, can you do a P0? Yes, you can. So you put T is 0 in there. Yeah, you can put T is 0 in here. You can get a P0. So this is not known in advance. In advance, okay, you have to solve this one to get this P. So why you need to resolve it now? So the best understanding of this box is you offline computing of the PT. Okay. Yeah, this is offline. I solved offline this PT already. Then I feed this one with the PT array already established. Okay, that was established. So that's the way to think about it. So I hope you appreciate that. Let me go back here, review this one again. That's the beauty of the everything. So you, in advance, you have Q, you have B, you have A. So you solve this PT in advance, okay? And solving this PT is from TF solving to T0, okay? And T0. So you don't have to do real-time computing. You can do offline, okay? Again, I keep saying that offline. So we are doing offline. Okay, this is a very important word. So you understand the optimal control, how it works. Okay. So whenever people say, oh, I'm doing online optimal control, then you should raise your eyeball and to have a closer look what they are doing. But fundamentally, we should not expect that kind of online computing because it's fundamentally of TPBVP problem. Your x and a lambda vector, you have an initial for x, a final value for lambda. So it's kind of half-half, okay? All right, I hope you're not confused by me. I said simulating will not work, which is so true, unless you compute PT offline, okay? Otherwise, you cannot see that. So it's a two different time error. The time error for this is from here, this T0 to TF. But this whole system here is a TF to T0. You can see how come you can integrate the differential equation in Simulink to reverse the time axis? No, you cannot. So here is a solution with different. So A is -1, x0 is 1. So it's starting from 1.0 here. 1.0. TF is 1. I only care about TF. Okay. And this is my control signal. It's optimal control, U star. This is my X star. Okay. And this is my PT. Okay, PT. So you can see the PT will always add up to 0. Did you see that? So PTF is end up with 0. Okay. Trajectories will change behavior when you put different weights on the control. Okay, on the control. So you can see when your control is a control penalty. Is a control penalty. The bigger the R will penalize you. The smaller R big, then U overall will be smaller. So in our case here, your U is bigger when R is smaller, which is reasonable, right? So again, this is try to minimize this thing, okay? This part of that. So I increase R, then I suppress the U. Suppress the U. Increase R, suppress U. So increase R, I suppress your U. Okay. But tuning this R, we see that my states will also behave different. But overall, my goal is not to do a terminal whatever. My goal is to this J minimum. Okay. J minimum. So this is LQR. Okay. For the finite time, TF is 1. So pretty nice, isn't it? Again, this figure, a lot of people is going to confuse. It's not going to work in Simulink, okay? No, it's just for illustration of original dynamic system, okay? And this is state equation. So this is nothing but first state equation, okay? So now time to talk about infinite time LQR problem, okay? What's the difference? Difference is in finite time LQR, basically you have time varying gain matrix KT. You have to build a KT as a lookup table to compute offline. Okay, compute offline. Okay, compute offline. But in reality, I want the system always be under control, so the TF to put into infinity is a reasonable way of doing it. So, but there are some fundamental difference in here. Okay, because the system is stable. Okay, so we should expect that when XTF goes to 0, the origin, okay, as TF goes to infinity. So it's a asymptotic stability guarantees this, okay. So because XTF is already there, so if you do XTS transpose XTF, the terminal cost, in fact, is always 0. So we can safely ignore it. So unlike in the finite time, I have to do this for the problem. No, we can just ignore it without it. So that is infinite LQR problem. It's a special case, of course. Yeah, special case. Okay. Special case. And we know for finite case, for finite time case, the U star optimal control is R inverse B transpose and PT, and so this happens to be a time varying gain with a full state feedback. So initially we try to solve optimal control signal, okay, but we end up with a control law, okay. So this is the beautiful side of this part. So interestingly, PTF is 0. Sure, it is 0. But we can say that T goes to infinity, this P will be a constant. It has to, okay? It has to. Because the P dot will be 0, okay? P dot will be 0. So each of these is like always constant. It's going to 0 to the infinity, okay? To infinity. So therefore, we should treat this side as 0, okay? So then we get to the ARE, okay, ARE. So it's a P bar is a steady state gain solution. This is P bar is when TF goes to infinity. So P bar A transpose P bar. So, but remember this P bar is symmetric, okay? So symmetric. So we don't have transpose on the P, okay? P bar B, R inverse B transpose and P transpose plus Q is 0, okay? So in this case, interestingly, because we are talking about send TF to infinity, okay, send TF to infinity, then this is going to be TF to infinity. So then we have this one, a constant matrix P bar. Therefore, I have a constant feedback in here. So important observation is for infinite horizon LQR, okay, then it ends up with optimal control signal as an optimal control law with a constant matrix, gain matrix. This is interesting. So this is my closed loop dynamics, okay, and this is my the optimal cost. Yeah, it's depending on what is your P and what is your initial state, where you started, okay, where you started. And that's reasonable, okay? That's very reasonable. So in infinite time LQR, we have to have this one is 0. If this is not 0, okay, then the J will be infinity. So we cannot solve this problem. It's not well defined. It's not well defined. So in other words, if you have unstable system, you should not. So it should be a stable system. Okay. And because of this one, we don't have to have a terminal cost. Okay. So this whole thing has to be sympathetically stable. Sympathetically stable. If not, you will send this one to infinity. Okay. If not. But we know that this cost already derived is supposed to be finite. Therefore, the x infinity has to be 0. Okay. All right. So no question. So this is an argument. Okay. So that is our infinite time LQR solution. Okay, LQR solution is like a full state feedback with the K. You might wonder, under this structure, where are all the pros? Okay, ask it. How robust? There are some dedicated discussion on that. Where are those pros? Okay, for SISO system, what is the gain margin, phase margin? All these questions are already answered in the literature, usually in the textbook. Let's do this one with an example. Okay, so this example is A, it's a -3. So this is a controllable form. So 0, 1. So this is a controllable control canonic form. Okay, control form. Control form. In this case, you can see you write this way is as if you are writing x1, x2, as if you write 1, 1, and here you have x1, x2. So this is the same as this one while writing. This is 0, this is 0. Okay, for U is the size of a single input, so this is a scalar. Okay, and of course we have a half in front. Okay, it's it's a tradition. Okay. So let's try to solve LQR. What is my infinite here? In MATLAB, this can be done easily. It's called just the LQR. So you give ABC, you give ABQR, or they'll give you a K. Okay, in the LQR sense. But let's do manually to see. We'll try to find a P. Okay, so but P is symmetric. So this one and this one should be the same. Okay, they're the same. But when we do that, we only have this actually 2 to care. Okay, 2 to care. And be careful, we use this symmetry here, so this should be the same. Okay. So then we split this one into matrix. So you can see here, you have PA, AP, okay, A transpose will become this. You have a PBRB is 0, 1. You have this. The Q here is identity matrix, Q. So in the end, we should write is 0. So this is the ARE, algebraic recursive equation. From here, you can solve all the P's, Pij. So you only need to have 3 parameters to solve. So basically, you got 3 equations. You only 3 equations. So then you get the P11, P12, and P22. That's it. So remember what we used in here. We only actually used 2 P11, P12, and P22. P12 and P22. We don't really need this one. Okay. So this is it. Minus P12, and this is minus P22. Oh wait. Yeah. This is right. So a minus sign here. Minus. Wait. This should have a minus sign here. Okay. I have a minus sign. Because I have a minus sign here. Okay. So that's why. So in the end, I find out I need a state feedback. This one and this one. The full state feedback. All right. So this is my control law. Okay. And it's static feedback gain. Okay. I can compute this gain in advance. Okay. So when you don't have MATLAB in front, you can compute this one just by expansion of this one. Again, for this 2x2 case, it's manageable. Okay. For this case, it's manageable. The 3-dimension probably is much harder. Okay. Well, so in the end, we are going to have a system like this. Okay, system like this. So, but you may wonder why this is the case, because you need to put the U inside. So you remember original system is here. You put the U in here. So x2 feed to x1 integration. So basically I see, so this is minus 3x minus 2. You should have minus 3x1 minus 2x2. That's why you have you have only a square root of 10 left, and so you have this one left, and your negative sign are all here. Okay, so that's the closed loop system. Closed loop dynamics. So the behavior of a closed loop is something like this. So you have x1, x2, you have, this is a phase plot. So your initial, when t0, you are here, so you will come to the equilibrium point. And while you come to the equilibrium point, your J is minimized as well. So you have multiple ways to go from here to here. So, but this, in this trajectory, in this phase portrait, this one, that is the LQR sense. Okay, LQR sense. Minimize the LQR. So that's one thing to control. So, but sometimes you are not so lucky to measure all of the states. What they do is that you, based on the output, but this could be I, then it's a full state. So, no, it's not interesting here. So we should not assume this is I. So you have Y. You do the same structure. So you have a gain, observer gain. And so this case, your LQR gain. So here is my U, okay? So here's my Y. So until here, yeah, this is my observer. Okay, observer. Then this is the LQR like we did. Okay, so it's called observer-based LQR. Okay. Okay. I think this is not hard for you at all. Okay. But of course, you need a CA as an observer pair. Okay. So of course, we already assume AB is controllable. Okay. That's it. So here is something a little bit more complex here. I hope you will not get very confused. Okay. So it's something called prescribed margin. Prescribed margin. So we basically do transformation that exponential of this. Okay. Like this. Okay. E alpha of t. So in other words, this x of t has to be decaying faster than this one. Otherwise, you're going to explode, right? So this uxt must be faster than this. This is growing, right? So what does that mean? What does that mean? That means in this pole plot. So this is real. This is imaginary. So previously, everything here. If I put something here, I shift my imaginary axis in here, okay, on this side. And the distance between here and here is actually alpha. Of course, this is 0, okay? So instead of pole placement, you place all your poles on the left of this dashed line, okay? Dashed line. Then I guarantee that my decay is faster than this guy, okay? Therefore, x tilde is still decaying, okay? Exponentially decaying. So this alpha, the width of alpha, is called the prescribed margin. Okay, this thing is called prescribed margin. But in a signal point of view, it's you pre-multiply e to the power of alpha t times x. Okay, okay. So on the other hand, I hope you understand there's something. Let's say you have f of t, you have f of s, they are Laplace transformation pair. What do you think about this? E to the power of at multiply f of t. What's that? I hope you understand. This is F. Wait. F minus A. Okay. Yes, S minus A. Okay. Okay. This is very easy to show by using the definition of Laplace transformation. Okay. It's very easy to show. Okay. Very easy to show. Yeah. So basically, I already told you about this idea. You shift this A to this side. So this is minus alpha. Minus alpha. Okay. Minus alpha. That is this one. Okay. This one. But anyway. So we try to do this one so that everything inside here will decay faster than the AT. Okay. So because I always use this scaling, and there's a quadratic form, so therefore you have 2 in here. Okay. So I'm going to put everything with a sub alpha. Okay. Sub alpha. Sub alpha. So I think we told you that when you put A plus alpha I, so how you do that? So you have A, so the eigenvalues of A is stable, then your poles on the left half there. Okay. But what if your eigenvalue A plus alpha I is like alpha is greater than 0? So as if we put a line in here, so this is minus alpha here, but all your eigenvalues in here, okay? If your eigenvalues all inside here, then this is also stable, okay? So how do I know all my eigenvalues lie in the left of the dashed line? Then we check this one is stable or not. So as if you have a line in here. Well, that's not important. The important thing is do this transformation. Okay, do this transformation. There's a physical meaning about the decay rate, prescribed margin, or decay rate. Decay rate. Okay, decay rate. So by putting this one in here, you are going to see that is equivalent to replacing A with A plus AI. So this is your new A, okay, new A. Basically, it's X tiered. Wait a minute. X tiered dot is A plus alpha I. X tiered plus B tiered. Okay, so that is the transformed system in the tiered. So if this is true, we're going to solve my optimal control law by solving this modified ARE and getting a P alpha, put it here. Then the closed loop system will for sure guarantees my optimal control guarantees decaying containing this one, not slower than this, okay? Not slower than this. So this is called LQR with a prescribed margin. So this is very interesting, right? So, let me see if I can change another color. So that's interesting. So people may say, hey, can we say I have a sector and here is distance alpha, I have sector, here is my theta. Giving alpha theta, can you make sure the prescribed region? Can you give me a prescribed region? And still satisfy LQR? So the answer is yes. This is a research topic. And a lot of, you can go and check D-stability problem, okay? Meaning you're giving a domain, okay? And make sure your closed loop poles are within this domain and still maintain the LQR, okay? So that's possible, yes. So let's run an example and we verify it. So I don't want to confuse you because there's lots of advanced topics because when you design the control system, you have lots of specifications, and not just here. Okay, you may have something else. You want to put some constraints on the LQR problem. Yeah. So let's talk about this is what. This looks familiar. Do you guys see this? What do you call it? Come on. This is a double integrator, okay? So you have a mass in here. So this is the floor. You apply AU, okay? Sorry. You apply AU. AU. And then you are going to have a movement of Y, okay? So that's why Newton's second law, but here M is 1, okay? Yeah, let's say M is 1 over A, okay? Okay, so then I'll put A in here. Okay, so then you have this double integrated system. Lots of mechatronic system is a double integrated system, okay? It's a motion control system. So you can add a spring damper, okay? Spring or damper into it. But doesn't matter, I can introduce you spring damper. So you are going to see it, okay? So let's do it. Original system in state space format is this is a position dot is my velocity. So this is velocity, this is the position. So position dot is my velocity, so that's why. And velocity dot is velocity dot is AU, okay, A and U, okay. And I assume that the control, the observation is CX. C is only position feedback. Not feedback, position is observed. Okay, so you can write A is A, B, C, and in this A, B, C you have Jordan. Okay, you have a Jordan form. Okay, but in the last row it's non-zero, so it's controllable, right? And it's also here it's non-zero, it's observable. So this is O and C both, okay, and this is also minimum, okay, realization. Now I want my y square. It's not x square, okay. So basically it's x1, y square is x1 square, okay, x1 square. So in this case, you can still write x1, x2. But here you should write as 0 as 1 and 0. X1, x2. That will give you x1 square. So therefore, this is my Q, okay? So Q is a positive semi-definite, okay? PSD. It's not fully positive definite because of 0, okay? But be careful, we have something here. So I want this one to be decaying at least not slower than E minus 2t here. No, actually, it's a square, so it's an E minus 1t. E minus 1t. This is my decay signal. Signal square will be E to the power of minus 3t, okay? Okay, let's try to solve and to see what's going to happen. So A, B, C, D. No D. D is 0. D is 0. Okay, I don't have D. Q is 1. R is 1. Alpha is 1. Okay, and this is controllable. This is observable. This is controllable. So then we write this one into our format here. This is my Q. Okay, this is R is 1. And this is alpha is 1 here. Okay. So let's move on. And so my LQR infinite time ARE. Okay, we can solve it. So we are going to have a P alpha in here. So then again, because of the structure in here, we have only care about these two. Okay, these two. So let's try to say solve this ARE. So it's a P A transpose P minus P B R minus 1 B plus Q is 0. Okay. So B is 0A times B transpose. Okay. No, transpose is here. Wait a minute. No. Yes, I'm correct. Okay. I'm correct. So this is correct. So this is A transpose. Be careful. What I'm saying is my A is actually 0, 1, 0. Okay, this is my A. But I need to plus alpha I, so this is alpha is 1, 1, 0, 0. So together you will get something. This is A plus alpha I. Okay. So then this is a transpose. Okay. So you end up with this one. This is A transpose. So this is this term. So then this one is R is 1, remember? So B, this one will give you 2 by 2, so it's like this. So you have 0 B, 0A. Here you have 0A. This is B transpose. Okay, this is B. So then you get a 0, 0, 0 until that last one is A square. Okay, square. So this is my Q. I told you. And this is 0. By arranging that, you are going to get 3 equations, and then you can solve the 3 solutions. Okay. But remember, we only need 1, 2, 2, 2. Okay. 1, 2, 2, 2. So here, what do we have? So finally, we get here to here. So we have minus. So this is my P1, P alpha 1, 2. So here is P alpha 2, 2. So I got my control law in here, full state. So but now I'm curious by putting this guy into my original control system. Okay. So put in, so this is my Y, this is my Y, Y dot. So put in, check whether we got it. So this is my A minus B R is 1, okay. This is B transpose. Yeah, PR in here. So in the end, you end up with this is still 0. Get this one. Then basically you are writing this is a controllable form. Controllable form. So in other words, this equation like minus A1 minus A2 will get a characteristic equation like this, plus A1 plus A2. Okay. By doing that, you can see what's the real part of that. You can do some manipulation. Your real part of the equation. Okay. Then this one is definitely less than minus 1. In other words, I said imaginary and real axis. In other words, you have a minus 1 here, and your two characteristic roots could be pair here. Okay, pair here. Guaranteed by the design. Say this here. But the question is, it's here, but why not here? You know? Okay. So in fact, if we check the angle here, okay, so it's guaranteed to be a 60 degrees angle. That's another interesting side. Okay. So I want to summarize what we did today regarding stability, guaranteed margin by the design. Well, there are a lot of questions we haven't addressed, especially like frequency domain interpretation. We haven't talked about it. Okay, and this actually covered in ME 212, robust and non-linear and robust and optimal control. Okay, so talking about the inherent robustness of LQR full state feedback. But what about you have a LQR plus observer? So looks like are you still getting the same level of performance like a full state feedback? A lot of people thought this can be guaranteed, but in 1978, John Doyle of Caltech, he wrote a paper for the first time to review the fact that by using observer, you are not going to enjoy the full state feedback robustness anymore. Okay, that's the beginning of the awareness of the loss of robustness of observer-based design. So in other words, you didn't buy the sensor to measure. You just use observer. Fundamentally, you are going to lose something. So that's the beginning of robust control. So hey, Karen, you are here. Just saw you. Great. Carlos also here. Well, let me pause to see whether you have some questions at this point. Next time, we are going to do. So today we basically covered quite a lot of things. Talking about ARE, talking about observer-based infinite. We went through an example, okay? Full state. We talk about you can use observer. Talk about ARE. Okay. We talk about prescribed stability margin. Okay. Yeah, we can also do output feedback using observer. Okay. But the warning is using LQR plus observer, you will have the issue of loss of robustness. But to understand the loss of robustness, you really need another lecture on the frequency domain interpretation. I believe John this book, I uploaded chapter 11. It has this type of discussion. But please pay attention about the loss of robustness issue when you introduce observer without full feedback. So next time, I hope we're not going to do final review. Okay, we're not going to do. We're not going to talk about the final exam. So please continue to do a jump-based chapter 11. So we are going to do to LQG. Okay. So a lot of people heard about common filter, but what is the LQG? LQG is linear quadratic Gaussian. Okay. GAUSSI Gaussian. I hope you have some basic understanding about it. So then you don't feel common filter is so sophisticated. It's actually within the linear multivariable control framework. All right. So I'll talk to you next time, and I'll let you ask a question. Do you have a question? So timing is good. If you don't have questions, so we're going to see you on Monday. I know on Monday we can have another help session on PS9, the last one. And also in PS9 discussion, you can talk about FISP presentation. So let me show you this again. This is the sequence. You already decided. Well, I'm going to announce to my lab, so you guys know who is going to talk first. So Kevin, you probably will set a role model for them. Then you'll have Carlos and Jack and Howie. I like this type of small class. And together we can really learn firmly of the basic knowledge of linear multivariable control. I'll check the sound for today and why this is not working well. I got a feedback from my mechatronics class. They also say the volume is too low. Maybe upload it to YouTube, it will be better. We'll see. Any questions? If you don't have, I'm going to turn off and I'll say goodbye to you. You guys take care of yourself and stay happy, stay safe, and stay creative. Okay. Bye-bye.
Bye-bye.
Okay. Bye-bye.
Bye.
Bye-bye.
Bye.
Bye.
Bye.